All right, so the next speaker will be Bastian Brandt with on QCD thermodynamics at non-zero isospin asymmetry. So please.
Right, thanks a lot. So can everyone see it now in full screen, I hope? Right. Okay, so yeah, thank you for the introduction and welcome everyone to my talk. Today I'm going to present, I would also like to thank the organizers for giving me the opportunity to speak here and present our results, of course. So today I'm going to present an update on our studies of QCD thermodynamics at non-zero isospin asymmetry from the lattice, and this is work mostly done in collaboration with Francesca and Gergő. I'm going to start with a very brief introduction into the topic before I summarize what we have found to be the continuum phase diagram from the lattice, and then I will come to new results concerning the equation of state, and then I will talk about, in my opinion, very nice application for the equation of state, and that's the possibility that the early universe might have passed through a pion condensed phase under certain circumstances, and then I will conclude. Okay, so well, you heard a lot about QCD at finite isospin density already. So we want to study the system from the lattice, and on the lattice, well, the lattice is usually set up in the grand canonical ensemble where the densities are traded for the chemical potentials. So in the QCD, we can actually try to find a suitable basis for our lattice QCD simulations, and a particular suitable basis for us is this one here, where the U, D, and strange quark chemical potentials are expressed through the isospin light quark baryon, well, and the strange quark chemical potential. And why is this suitable? Well, we can directly see that if either this light quark baryon or the strange quark chemical potential is non-zero, then we have a complex action problem and we cannot do simulations anymore. On the other hand, if both are zero, we are at pure isospin chemical potential, then we have a real action and actually can do our simulations. So yeah, QCD at pure isospin chemical potential is also interesting in its own right. We have heard already about the phase diagram. So we have this standard hadronic phase here. We have the quark-gluon plasma phase here. And then if we increase the isospin chemical potential, we will somehow go into this phase of condensed charged pions, the Bose-Einstein condensation phase here. If we further increase our isospin chemical potential, then it is likely that we at some point will pass into a BCS superconducting phase, where instead of our tightly bound pions, we will then have well, rather expanded pseudoscalar Cooper pairs. Right, so the Bose-Einstein condensation is accompanied, as Massimo has very nicely summarized, by the spontaneous breaking of this remnant of chiral symmetry if we are at finite isospin chemical potential. And this is what we would like to observe on the lattice. However, this is also one of the biggest problems because, well, I mean, accompanying this spontaneous symmetry breaking is a Goldstone mode, and this leads to a low mode in our simulations, which is making the simulations extremely hard. And at the same time, well, lattice QCD is always set up in a finite volume, but we all know that we cannot observe the spontaneous symmetry breaking in a finite volume as long as the symmetry is still intact. So these are the problems that we are facing, and we can actually solve both of them by introducing a regulator that Jens also mentioned already, the so-called pionic source. And of course, so we are simulating at non-zero pionic source, and eventually to obtain physical results, we then need to remove the regulator. That means that we are extrapolating our results to zero value for this regulator, to zero lambda. The reliable extrapolations are then actually the main task for the analysis, and the reason is, so what you can see here are results for the chiral condensate at non-zero values of lambda, is the strong lambda dependence for a lot of observables, in particular the interesting ones. And you can clearly see that from this plot that if you try to extrapolate this somehow to lambda equals 0, this is a very long extrapolation and will include large systematics. So what we did to basically overcome this problem is we developed an improvement program. And so these blue points here are actually the results or at finite lambda from this improvement program. And then we can do our lambda extrapolation, and you see that it clearly becomes flat, and you can do very reliable extrapolations. So that's basically the basis for all our lattice studies here. And from now on, I will only present results where these lambda extrapolations have already been done. Right, so let me start with my summary concerning the continuum phase diagram. So this is our general lattice setup. We are using physical quark masses and pion masses, of course. We use improved actions, but that's just a side remark. So let's start with discussing the phase diagram that we get. So first, let's start with the pion condensation phase boundary. Here, the order parameter is the renormalized pion condensate. And I'm showing a plot here from an n=6 lattice. So this is the temperature axis here. This is the isospin chemical potential axis. And well, the phase boundary is basically, the phase boundary line is basically the line where this pion condensate becomes non-zero. So I can directly read it off from here. And what is shown on top is already the continuum extrapolation of this line. Right, so we could also ask what is the order of this transition to the pion condensed phase. And what we can do, and we did that at a temperature which is actually down here, is to do a finite size scaling analysis. And what I'm showing you here is the comparison of our results with O2 scaling, and you can see a very good agreement. So that means that indeed, as expected, we observe this transition to be a second order transition in the O2 universality class. And that's true at least here, right? So whatever happens here, we cannot say yet. Okay, so we can also look at the prolongation of the chiral crossover into this parameter space here. And here the relevant observable is the chiral condensate, in particular its inflection point. And then again, we can draw the resulting curve. And at some point, these two curves will meet, and this is what we call a pseudo-triple point. Well, it's the meeting point of a crossover and a second-order phase transition. So if this would be a true phase transition, this would really be a triple point. But so this for us calls for calling this a pseudo-triple point in this sense. Also interesting is that from this point on, the two phase boundaries coincide, and we really have the pion condensation occurring at the same point where chiral symmetry is restored. Right, so the question, of course, is where is the BCS phase in this plot here? And well, at least from the lattice, that is still work in progress. So unfortunately, we don't know that yet. And this is also a very interesting question. And I would be happy to discuss about this later. Well, okay, so let me now come to new results. That were the results for the phase diagram. But if we want to describe at least this non-zero isospin part in any physical system, we need some input. And what particularly important input is the equation of state. So we would also like to determine this equation of state now at non-zero isospin chemical potential. Let's start at t=0. And in this case, we can actually compute the pressure and the interaction measure from a suitable interpolation of our isospin density. So we have to compute that from the lattice. And well, this is actually, well, we can do that, but at exactly t=0, this is unfortunately impossible, because you should note that in our lattice simulations, we never have an exact zero temperature. Okay, so what we typically do is we use a very large temporal extent so that the temperature is approximately zero, so that we can be, well, sure to some extent that thermal effects are suppressed sufficiently. And what I'm showing you here are the results from such a simulation. However, you can see that the isospin density is not going to zero at the transition, which is here, but it still retains a non-zero value. And this is really due to the fact that we are at non-zero temperature and also that we are at non-zero volume. So that's an additional effect, but also this effect sets in here. So of course, if you want to determine the correct equation of state, this is quite a problem, but we can cure that by using chiral perturbation theory, which we believe to work very well in this region here at zero temperature. So what we do is we perform a fit to our lattice data, in particular to these 2 points, using leading order chi-pt, and we actually see that this works very well. So this is the value that we get from this grid for the pion decay constant. And then to go to larger mui's, we actually match this fit to a spline interpolation for the rest of our points. Okay, nice. So having this interpolation, we can go on and extract the equation of state. So what I'm showing you here is the pressure and the interaction measure versus the isospin chemical potential, and these dashed lines here are the leading order chi-pt results that you've seen in Jens' talk already. And you see that there is this very nice agreement already with the leading order, and the interaction measure is actually doing something interesting that I would also like to point out. So first, it is positive; it's starting to be positive, but then at some point it's turning around and starting to get negative the more we go into this pion condensed phase. So this agreement I already mentioned. So there's one caveat here. This is actually has so far only been done for a single lattice spacing. So we are currently working on the continuum limit, and this is really work in progress. But these zero temperature or almost zero temperature simulations are not so easy. So this is what we are currently working on. All right, so let's now move on to finite temperature or non-zero temperature. And in this case, the pressure and also the interaction measure are quite well known in the continuum already. So we can just use those and focus on the modifications of the pressure and the interaction measure due to the isospin chemical potential. So we are considering this ui equals 0 subtracted quantities here. And well, the computation of the pressure part is rather straightforward. It's basically the same what we have done before. So we just have to compute this integral over the isospin density. But the interaction measure is actually a bit more tricky. So there are actually two methods that we can use. The first is probably the first thing that comes to mind is the generalization of the so-called integral method to determine the equation of state from the lattice. And this is what we had in mind first. However, here there is a problem that this really leads to large uncertainties, and the problem are these μi equals 0 subtractions. So in our expression for the interaction measure, there is also, for instance, the gluonic action density appearing, and what I'm showing you here is the result from this lambda extrapolation for this quantity. But now we also have to subtract the mu equals 0 value, which is very close, and then it's obvious that the result will have really large error bars, and these error bars actually propagate to our interaction measure. So fortunately, there's also another option, and that is to do a suitable two-dimensional interpolation of our isospin density, and actually this turns out to be more accurate, and I will show you the results of this method now. So first of all, we have to express our interaction measure in terms of the isospin density here. And so that, well, it's basically done in this formula. So if we have a two-dimensional interpolation of our isospin density, then we can compute all these terms and compute our interaction measure. So of course, well, we want to have a model-independent interpolation, and that's quite difficult. So what we do here is we perform spline fits, but just choosing one particular spline fit would already be sort of a model. So we are trying to avoid that. So what we are doing is we are doing a Monte Carlo over all possible spline fits, and we weight them by using the Adhikari information criterion. So we favor those that have a small value for this Adhikari information criterion. This is also a particular choice, but this is what we do here. Okay, so what I'm showing you now are these interpolations already after the Monte Carlo. So even this Monte Carlo error here is included. And you can see that they really very well describe the data. So that's now for NT equals 6. And even in this region here, and this is actually the region where the phase transition occurs. Here we expect, actually, we are in a finite volume, so we do not expect a kink, but we expect a very rapid change of the isospin density. But even here, this interpolation is able to capture the behavior of the isospin density that we observe from the lattice. Okay, and I'm showing this here, sorry, versus the isospin chemical potential and the temperature in this right plot. All right, so now that we have these interpolations, we can again go on and compute the equation of state. So what I'm showing you here are now results on an NT equals 8 lattice, and I'm showing you results for the pressure, the interaction measure, the energy density, and the entropy density. Of course, always mu I equals 0 subtracted. And I'm comparing that to the results at 0 temperature here. These are the gray curves. This is now a very small temperature, and you see that the curves are still rather close. You can also see most of the features here. So here the curve is actually, the T equals 0 curve is actually 0. But you already observe some temperature effects as expected, and now we can increase the temperature. And well, I'm showing this here for two other temperatures. Here you can still see some effects due to pion condensation in the equation of state. But then if we go to 168 MeV, then these effects are gone, and well, all of the quantities are just raising with increasing chemical potential. We can do that for different NTs, and this is what we have done. So what these different colors are just now different MTs, and we are currently performing this continuum limit. So this is work in progress, and yeah, soon there will be results. Right, so something else that we can do with this two-dimensional interpolation of our isospin density is we can actually revisit the phase diagram and determine the phase diagram in terms of our isospin density. And the result for NT equals 8 is shown here. Please do not look too close into this region here. We don't have lattice results here. Okay, so this is just to guide the eye that somehow we have to reach this point at 0, 0 down here. But this is just linear. Okay, so this is not really a lattice result. Okay. So now we can again do this for different MTs, and also here the continuum limit is in progress. And of course, we can also look at the crossover line in this parameter space. And then again, this is not really a lattice result yet, so we have to do more there. And then we can compare this phase diagram with the phase diagram in the new IT plane, and we see that apart from this region here where nothing happens due to the silver blaze, the two are actually very similar. So once there is the onset of pion condensation, there is a very rapid increase, and then it soon starts to level off. That is seen in both plots. And also the chiral crossover is very flat in both of the cases. All right. So let me now come to this idea that the early universe might have, or this possibility that the early universe might have passed through a phase with pion condensation. And this is work done together in collaboration with these people here. Actually, what I'm showing is mostly the work done by Volodya. Well, we have recently published a paper on this. So what we want to describe is the evolution, or what we want to investigate is the evolution of the early universe in the QCD-dominated era, which is somehow, maybe this era here, if I'm not mistaken. And yeah, in this era, the universe undergoes an isentropic expansion, where the trajectory in this parameter space here is governed by these conservation equations here, where we have the baryon density, the charge density, and these lepton densities, and they are normalized by the entropy density. And then on the right-hand side here, we have the baryon asymmetry and the lepton flavor asymmetries. We would also have a charge asymmetry, but this is constrained to be 0. And now also for these two quantities, we actually have constraints. So basically from the cosmic microwave background, so this parameter B here actually has to be rather small. And we also know that the sum of these lepton flavor asymmetries has to be smaller than this value here. So it's also rather small, I would say, even though considerably larger, of course, than the baryon asymmetry. However, if you look at these numbers, then it's clear that both the baryon chemical potential and the charge chemical potential are almost 0, or at least close to 0. And that means that if we want to write down the equation of state governing the evolution of the early universe in this region here, we can actually use as the QCD part the lattice QCD results and vanishing chemical potential may be combined together with a Taylor expansion. And here, well, we've just modeled these, the leptonic part and the photon part by an ideal gas in the following. So that's, of course, an approximation to the true equation of state, but it might be very valid in this region here. Now, if you forget about this bound for a moment and just take larger values, then it has been shown that if the sum passes 0.15, then actually we can enter the pion condensed phase. Okay, so of course, well, we know that this boundary exists here, so this is not likely, but this can happen in this particular case. Now, while the sum of the lepton flavor asymmetries is constrained, actually the individual lepton flavor asymmetries are not. So, sorry? Okay. So actually the individual lepton flavor asymmetries are not. And one of the reasons is that actually neutrino oscillations do not set in above 10 MeV. And that means that those not necessarily have to be equal. All right, so what we would like to try now is we would like to try to see how the evolution of the early universe would have undergone if these individual lepton flavor asymmetries vary. And in order to do that, we need to do something about this equation of state. So actually, we would like to take it from the lattice, of course, but then we are facing a system with, well, more or less a pure charge chemical potential. These values also might be non-zero, but this will be the dominant term. And if we just plug that in, then we actually see that we have a Sine problem. Okay, the reason is that the d core chemical potential is not minus du core chemical potential. So we are not just at non-zero isospin chemical potential and pure isospin chemical potential, but we also have another component.
Bastian?
Yes.
Time is running out in a few minutes.
Right, thanks. I will hurry then. So so we cannot do that yet. This is work in progress. So what we could do in the meantime was to construct a simple model which captures the pion condensation features. And what we did was we cooked up a hadron resonance gas where the pion contribution is actually replaced by such an effective mass model for the pions and then matched it to lattice QCD. What I'm showing you here, and I will be a bit brief, is a comparison to lattice QCD. Basically, there is some reliability window that we can extract from that. And we will try to stay within this reliability window where this model really works well. Okay, so what we do now is we scan in these individual lepton flavor asymmetries by keeping the sum of them actually equal to 0. Okay, and then we compute the trajectories that we have from our universe. Some results are shown here where this is 0. Actually, this does not depend much on this difference. And then you can see that if this sum is large enough, then we can actually enter the pion condensed phase. And where these lines turn dashed, this is the region where we do not trust the model anymore. Okay. Actually, we can make this a bit more quantitative. And then we see that pion condensation can be realized if the sum is bigger than 0.1. Actually, yeah. So outside of the pion condensed phase, we actually reproduce other results from another model, which does not have pion condensation built in, so they cannot go into this pion condensed phase. But then they also see very similar results for this boundary here. So let me just very briefly, before I summarize, discuss the effects due to that. So of course, this passing through the pion condensation phase will affect the equation of state strongly, and some results for this equation of state are shown here. And through this equation of state, it will, of course, also change other cosmologic observables. Particular to example are the relic density of the primordial gravitational waves, and also the fraction of primordial black holes, in particular in this region where they are heavier than the solar mass. So, of course, these are model calculations that I'm showing here, but if I fix the parameters of the models, then I can clearly see a strong effect due to this change of the equation of state. Right, so the hope is that at some point this can be pinned down by experiments. So let me just wrap up and let me be a bit quick about it. So from the lattice point of view, what is well known is the phase diagram. Soon to come is the equation of state. But there are a lot of open questions, so there's lots of room for new studies. Interesting applications are waiting, to my opinion. And yeah, I'm happy to answer questions also later.
Okay, thank you very much, Bastian, for your nice talk. We have time for 1 or 2 short questions regarding specifically this talk.
I raise my hand again, Anderson.
Yes.
Can I ask?
Yes, sure.
Oh, thank you. Brent, nice talk. I have a brief comment and a question. Mm-hmm. You are always comparing the lattice results with KPT, but last year we have shown that NGL has done a good job using the pion mass that use on the lattice. Mm-hmm. So, and second one, I have a question about the lattice data, and I have seen in your data a few points in. I'm talking about zero temperature.
Mm-hmm. Okay, sure.
And I have seen a behavior in isospin density when you show the lattice data t equals 0 that I compare in last year, and I'm doing SU3 calculation now. Then we in NGL, we are in agreement with KPT, because if you use in the isospin density, there is like a kind of non-monotonic behavior. Mm-hmm. And you cannot find this in the models. I would like to understand if it's a lattice problem or there are physics behind this.
Well, to answer that question is non-trivial in the sense that, well, I mean, first of all, this is at finite lattice spacing. So it could be that this is a lattice spacing effect. However, for these values of the isospin chemical potential that we have here, I would be surprised. They are actually not very large in lattice units, and that's the relevant thing for that. Apart from that, I think we have, well, of course, there could also be effects due to finite volume, but also those I don't think should be very large. But apart from that, I would say that we have our effects rather good under control. So, well, I would never say never, but apart from the continuum extrapolation, I would be surprised if there is a strong effect which is really driving this like up by some larger amount. I mean, it might be that this change, well, that this might shift a bit. Well, these are of course estimates for the error bars, right? So there could be a 1 sigma deviation, but then I would not expect it to be like up here or something like that.
Yeah, because this will affect a lot the equation of state. So we are not seeing this effect on the models. So when you are this on the lattice, this lack of discrepancy needs to be understood, because the equation of state there is a kind of non-monotonic behavior feeling there, right? I guess it's important to try to understand, because in the models in
I mean, it's not non-monotonic in the sense that it changes monoticity.
Yeah, but you have few points in NI. So you have you going up, going down, and these go to the energy density and fall in equation of state behavior.
I mean, okay, we are not going down. So first, I would like to say that we are never going down in the isospin density. Okay, so we are always going down. It's true that the curvature changes here. That is true. I can agree with that. And of course, this will have effects for other quantities. Yes, that is right. I completely agree with that. But yeah, I mean, we will also have to see what the continuum brings. So answering this question like in full now is just not possible for me. But as I said, I would be surprised if this changes dramatically. So some kind of behavior like this, I would say should remain in the lattice data. And then the question is, where does this come from? Of course.
Okay, thanks.
That's a different question.
Okay, that was one question and one comment. So I think the remaining questions will be for the discussion session.